In this example problem, we're going to first construct a 5-point moment axial load interaction diagram without phi factors. We'll find our 0 moment point, our balance point, tension controlled point, where our strain in our tension steel is equal to 0.005, pure moment capacity where we have no axial load, and 0 moment tension point. So we'll then add our different phi factors and minimum eccentricity limits to this diagram. So we'll add our phi factors for our compression controlled and for tension controlled, and our minimum eccentricity limit, which will cap our pure compression point. And then finally, we will look at if our column is biaxially loaded. So we want to find our column capacity phi Pn if we have an eccentricity in both the x and the y direction. So we have a moment in the x and the y direction caused by our axial load. Our section, we have a 12-inch by 12-inch square column with 8 number 6 bars evenly spaced around the cross section, where our top and bottom steel are spaced 2 inches from the top and bottom faces, and our center steel spaced in the middle, so 6 inches from the top and bottom faces. We'll need our beta 1 for this example. So we can find beta 1 using our ACI expression, just 0.85 minus 0.5 times our F prime C, which is 5 KSI minus 4, which will give us 0.8, which is greater than 0.65. So we can use our beta 1 equal to 0.8 for this example. The first point that we're going to look at is our pure compression point. So we have no moment in our section. For this point, we're going to assume a strain of 0.003 across the whole section depth. So that means that we have all of our layers of steel are going to be yielded. And for our compression point, we're going to use 0.85 times F prime C. The 0.85 accounts for the difference between our cylinder strength and our in situ strength, and it also allows us to stay consistent with the rest of the points where we use our stress block approximation, where we have 0.85 magnitude stress. So here, we can sum all of our different force components, and we'll have the capacity in pure compression is going to be equal to N equal to 0.85 times 5 KSI concrete times our AG, which is 12 inches times 12 inches, minus our total area of steel. So we have 8 number 6 bars, and the number 6 bar has an area of 0.44 square inches. And then we add in our 8 number 6 bars that are all yielded 60 KSI. So we'll get an N here equal to 808.2 kips. So this axial load with our moment equal to 0 will give us our first point on our moment axial load interaction diagram. We can also note that our curvature at this point is going to be 0, which is the slope of our strain in our strain diagram. We can also note that since our section is symmetrical and is symmetrically reinforced, the plastic centroid is going to be located at the centroid, or at the geometric centroid. So our plastic centroid is just equal to our total height 12 over 2, which will be 6 inches. So we'll use this plastic centroid moving forward. Our next point of interest is going to be our balance point. And our balance point is when our bottom layer of steel, our layer 1, yields when our concrete crushes at the top. So when we have a strain of 0.003 at the top and a yield strain at the location of our tension steel. So we can find our neutral axis depth from similar triangles here. So we'll just do our C is equal to our D1, which is 10 inches, times 0.003 divided by 0.003 plus our yield strain, 0.0021, and we'll get a C here equal to 5.93 inches. We can then use this C to find our strain in all of our layers of steel, which we can use to find the stress in our layers of steel and the forces in our layers of steel. And we can also use our C to find our concrete force. So first, let's find the strain in our layers of steel. So our epsilon S3, the strain in the top layer of steel, is going to be 0.003 divided by C times C minus D, which will give us a strain here of 0.0020. So this is less than yield, so we can take this strain times the modulus to find our stress. So we have our stress is equal to our strain times our modulus, 29,000 KSI. Will give us a stress in our steel of 57.7 KSI. We can then find the strain in our middle layer of steel. So this will be equal to 0.003 divided by our C, 5.93, times C, 5.93, minus our D2, which is 6 inches. So we'll get here 0.000035 strain. And we can see that our C is less than our D. So we had initially assumed that this layer was in compression, but we can see that it's actually in tension. So we'll take our strain here times our stress, or sorry, times our modulus to find our stress. So 0.000035 times 29,000 KSI will give us a stress here. I'm sorry, that should be negative. Will give us a stress here in our second layer of negative 1.03 KSI. And we'll just remember that this is in tension. So when we add up our components, we'll need to remember that's in tension. So then we can find all of our different force components. So we'll take our stresses times our area. So for our top steel, we have 3 number 6 bars times our stress, 57.7 KSI, which will give us a force of 76.1 kips. And then our middle steel, so we have 2 number 6 bars times our stress, negative 1.03 KSI, which will give us a force here of 0.9 kips. Then we can find our concrete force. So 0.85 times 0.8 times 5 KSI times C, which here is 5.93, times our B, 12 inches, will give us a compression force component of 241.9. And then our tension force here is 3 number 6 bars that are yielded. So we'll get a tension force of 79.2 kips. If we add these force components, so we'll have our N is equal to, and this would be CS3 plus CC plus TS1 and then plus CS2. So we'll have 76.1 kips minus 0.9 kips plus 241.9 kips minus 79.2 kips will give us a value here of 237.9 kips. So this is our axial load here, or at our balance point. So we'll next need to use these forces to calculate our moments. And before we do that, we'll need to calculate all of our different lever arms. So we'll find first our concrete lever arm. And our concrete lever arm here is going to be equal to 6 inches minus beta 1 times our C, 5.93 inches, divided by 2, which will give us a lever arm here of 3.63 inches. We can then find our top steel lever arm. So this will be 6 inches minus 2 inches to give us 4 inches. And then our bottom steel lever arm, so 10 inches minus 6 inches, which will be 4 inches. And these two lever arms are going to remain the same for all of our different points because the location of our steel isn't going to change. And we're summing our moments about the plastic neutral axis, and that's not going to change at our different points either. So the only point that we'll need to recalculate is the concrete lever arm for each additional point. You can also see that our center layer of steel, our CS2, is applied here through the plastic neutral axis. So we don't have any lever arm and we don't need to include that in our moment calculation. We can use these lever arms then with our forces to find our moment. So here we have 4 inches times 76.1 kip plus 3.63 inches times 241.9 kips, and then plus our 4 inches times 79.2 kips, which will give us a total moment of 1,499 kip inches. Just also notice that we're summing moments about our plastic neutral axis, so think about how our different components are going to add together. So here you can see that all of our forces are going to cause a counterclockwise moment. So that's why we're able to add all of our different components together. If we had one moment that was going in the other direction, we just have to subtract it. We can next calculate our curvature based on our strain diagram. So we'll have 0.003, which we know, divided by our C to find our curvature. So 0.003 divided by 5.93 inches will give us a curvature here of 5.1 times 10 to the negative 4th radians per inch. So this is our curvature and our moment and our axial load we found on the previous slide. The next point that we're going to find is our tension controlled point. And this is when the strain in our tension steel is going to equal 0.005 when the strain in our top fiber of our concrete equals 0.003. 0.005 is the current ACI tension controlled limit. So this is the strain where we can use a phi factor of 0.9 compared to our compression controlled limit for this section where we can only use a phi of 0.65 for the rectangular or square section shown. So again, we can use similar triangles to calculate our C based on our two known strain values. And we'll find our C is equal to our D, 10 inches, times 0.003 divided by 0.003 plus 0.005, so 0.008, which will give us a C here of 3.75 inches. So we can use this C then to calculate our strains and stresses in our different layers of steel. So in our top layer of steel, we'll have our epsilon S3 is equal to 0.003 divided by C, 3.75, times our C, 3.75 minus our D3, 2 inches, which will give us a strain here of 0.0014. We can use this strain to then find our stress. So the stress in our layer of steel is just our strain times our modulus, so 0.0014 times 29,000 KSI will give us a stress here of 40.6 KSI. And then we can find the strain in our middle steel. So we'll have a strain here of 0.003 divided by C, 3.75 inches, times C minus D. So again, here I'm assuming compression, but you can see that we'll be in tension. So just kind of note which way we're assuming, and then we'll have a negative sign. But our C minus D is 3.75 minus 6, which will give us a strain here of negative 0.0018. So we can use this to find our stress times our modulus, 29,000. And we'll find our stress to be 52.2. We can then use all of these stresses to find our different force components. So our force component in our top steel, we have 3 number 6 bars times our stress will give us a force component of 53.6 kips. Then our middle steel component, we have 2 number 6 bars times our stress will give us a force of 45.9 kips in tension. We can then find our concrete force component. So 0.85 times 0.8 times 5 KSI times our C, 3.75 times B, 12 inches, will give us a force component here of 153 kips. And our tension steel still yielded, so our TS1 is going to be the same as for our previous point, so 79.2 kips. We can then add up all of these components, and we'll get our N. So again, this will be CS3, TS1, and CS2. So our n is going to be equal to 53.6 kips plus 153 kips. And then we subtract off our tension components, so minus 45.9 kips and then minus 79.2 kips will give us a n here equal to 81.5 kips. So this is our axial load at our tension controlled point. We can next use these forces with our lever arms to calculate our moment. So first we'll have to find our concrete lever arm. So our concrete lever arm, so Y CC, is going to be equal to our 6 inches minus beta 1 times C divided by 2. It's going to give us a lever arm here of 4.5 inches. So our top and bottom steel lever arms are going to stay the same because these layers are in the same location as the previous point, and we're still summing moments about our plastic neutral axis or plastic centroid. So those lever arms aren't going to change, so we can keep those. So we can find our moment, and our moment is equal to 4 inches times our force, 53.6 kips, plus our lever arm for our concrete, 4.5 inches, times our force in our concrete, 153 kips, and then plus our lever arm for our bottom steel, our tension steel, 4 inches, times our force, 79.2 kips. And we'll get our moment here to be 1,219.7 kip inches. So this is our moment for this point. We can also find our curvature, which will just be 0.003 divided by our C, 3.75, which will give us a curvature at this point of 8.0 times 10 to the negative fourth radians per inch. So this is our curvature at our tension control point. Our next point is our pure bending point. And for pure bending, we have an axial load of 0 kips. We know in our strain diagram that our top fiber strain is going to be equal to 0.003, our AC assumption, but we don't know another strain value. So we'll need to calculate our neutral axis depth, or C, based on our equilibrium expression. So we're going to first find all of our different force components in terms of C, and then plug these in to our equilibrium expression and solve for C. And we're going to assume that the middle layer of steel and the bottom layer of steel have both yielded. So that'll affect our force components, make it a little easier. All right, so, and we'll need to go back and check those assumptions then. So first we can find our top steel force. We can remember our top steel strain we can find dependent on C. We can take our strain times our modulus to find our stress, and then our stress times our area to find our force. So for us, we'll have a CS3 is equal to 0.003 times 3 times 0.44 square inches times 29,000 KSI times C minus our D over C. And here we'll get our CS3 to be equal to 114.8 times C minus 2 inches divided by C. We can then find our middle steel force. So our middle steel force, T, S2 is just 2 times 0.44 times 60 KSI. Will give us a force here equal to 52.8 kips. We can find our concrete component. So 0.85 times 0.8 times 5 KSI times 12 inches times C is going to give us 40.8 times C. And then our tension steel component is going to just stay the same. So it'll be 79.2 kips. We can then plug all these into our axial load expression. So we'll have our N is equal to compression positive 114.8 times C minus 2 over C plus 40.8 times C plus minus, because we have a tension component here. So minus our 52.8 kips, and then minus our 79.2 kips, and this is all equal to 0. We can simplify this into a quadratic equation, and we'll get 40.8 C squared minus 17.2 C minus 229.6 equal to 0. And then using our quadratic equation to calculate C, we'll get C equal to 2.59 inches. So we'll use this C to find our unknown forces and check our assumptions on the next slide. All right, so now we can use that C to calculate our different forces and our lever arms, and ultimately calculate our moment and our curvature. So we can start by finding our concrete lever or concrete force. So our concrete force is just equal to 40.8 times C, so times 2.59. And we'll get our concrete force then to be 105.7 kips. We can find our lever arm. It's just going to be equal to 6 inches minus 0.8 times 2.59 divided by 2 will give us a lever arm of 4.94 inches. We can then find our top steel force. So CS3 is going to be equal to 114.8 times 2.59 minus 2 divided by 2.59 will give us a force in our top layer of steel of 26.1 kips. We know our bottom steel force already, and we know our bottom steel lever arm already, and our top steel lever arm. So then we can use these forces and lever arms to calculate our moment. So our moment here will be equal to 4 inches times 26.1 kips plus 4.94 inches times 105.7 plus 4 inches times 79.2 kips, which will give us a moment here of 946.7 kip inches. So this is our moment at this point. We can find our curvature and also check our strain in our steel layer too, using our strain diagram. So our curvature is 0.003 divided by 2.59, which will give us a curvature here of 11.6 times 10 to the negative 4th radians per inch. And then finally, the strain in our middle layer of steel is 0.003 divided by 2.59 times 6 minus 2.59, which will give us a strain of 0.0039. So this is greater than our yield strength, yield strain in our steel. So we know that this assumption checks. So for pure bending, we have now our moment, and our axial load here is equal to 0 kips. So this is our next point on our moment axial load interaction diagram. The final point that we're going to find on for our moment axial load interaction diagram is our pure tension point. And in our pure tension point, we're going to have a constant strain across the cross-section depth. And we're assuming that the strain causes all of our layers of steel to yield. We're not going to have any concrete force component because our concretes we're ignoring in tension. So we'll only have our tension component from our 3 layers of steel. So our N here is just then all our total steel. So 8 times 0.44 square inches times 60 KSI, our yield strength. And we can find our N here to be 211.2 kips. We know that our moment's 0 at this point and our curvature is 0 at this point as well. We can put these points together to develop our moment axial load interaction diagram with our 5 points shown. So our 0 moment, our balance, our tension controlled, pure moment, and 0 moment tension. We can also include our phi factors. So our phi factors will be dependent on whether we are tension controlled or compression controlled. When we're at our pure tension, pure moment, and tension controlled point, we're going to be tension controlled. So we'll have a phi of 0.9. And when we are at our balance point or our pure compression point, we're going to be compression controlled. So we'll have a phi of 0.65 for our square column. If we had spiral reinforcement, we would have a phi of 0.75 for our compression controlled region. When applying our phi factors, we take both of our moment and our axial load times phi to find our new point. And note that this table includes phi factors, but it doesn't include our minimum eccentricity limit yet. We're going to calculate that on the next slide. Here we can include the ACI minimum eccentricity limit. This limit accounts for the fact that we're never going to be able to apply the load directly in the center of the column. There's always going to be some kind of eccentricity that that'll happen with the load, which will cause some kind of moment. So we need to account for that with our minimum eccentricity limit. We can find our capacity then for just our square column without spiraled ties to be phi pn is 0.8 times 0.65 times 0.85 times 5 ksi times our 12 inches times 12 inches, our gross area, minus our 8 times 0.44 square inches, our area of our steel. And then we add in our 8 times, sorry, I put a bracket too soon. We add in our 8 times our 0.44 times 60 ksi. And this will give us a value of 420.3 kips. So this is our pure compression capacity, including the minimum eccentricity limit. So we can include that in our table and plot our factored moment-axial load interaction diagram here. You can see that if we're only calculating these 5 points, we want to connect our lines here with a straight line, just to make sure that we're not making any incorrect assumptions on what happens between these points. If we were to plot more points, though, we can see our factored moment-axial load interaction diagram shown here. And if we include the minimum eccentricity limit, we'll get a flat cap here at the top of our diagram. So this is with our minimum eccentricity limit. So you can see with these diagrams then we can figure out where our different load combination points, so from demand, would fall. And we want to make sure that our column has our different load demand points contained within our curve that we developed. That'll be a satisfactory design. The last part of this problem is to calculate our capacity, phi pn, if we have an eccentricity, if the load is applied with an eccentricity in both the x and the y direction. So this will cause both bending about the x and the y axis. So what we'll do first is we're going to find all of our forces in terms of C. We're going to assume that the top steel yields and the bottom and middle steel do not yield, and we'll just need to check those assumptions after we calculate C. So we can find our top steel force. So we have our 3 number 6 bars that are yielded to find our force. Our middle steel force, which we're assuming is in compression. And so just our 0.003 times our area times our modulus times C minus D2 over C to find our middle steel force. We can find our concrete steel force, same as before, and our bottom steel force. So we can add all of these components together to find our N in terms of C. Next, we need to find our moment in terms of C. So we'll have our concrete lever arm, which is dependent on C. And we can just take our different force components. So lever arm times force, lever arm times force, lever arm times force for our 3 different forces. And then we can simplify this equation a little bit as shown on the next line. We know that our moment is going to be equal to our force times our eccentricity. So what we're going to do is set our moment equation that we found on the previous slide equal to the force equation on the previous slide times the eccentricity in one of our directions. So we'll choose EX as the first direction, and then we'll need to do the same thing for our EY. So here we just have our moment equation times, or set equal to our force equation times our eccentricity. And here C is the only variable, so we can check and make sure that, or we can calculate our C based on this equation. So from here, we need to verify all of our initial assumptions were correct. So we can find our top steel, middle steel, and bottom steel strains. We'll find that our top steel has yielded, our middle steel has not yielded, which we assumed, and our bottom steel hasn't yielded. So all of our assumptions are okay. If one of our assumptions wasn't okay, we would need to go back and, I guess, yeah, correct the assumption. So whether it be that our one of our layers of steel had yielded or hadn't yielded, we would just need to correct the assumption and correct our moment and axial load equations. We can then use our C to find our axial load. So just plugging in our C into our axial load expression, we can find our axial load to be 461.4 here. And because our tension steel hasn't yielded, our phi factor here is just 0.65. So to find our phi PNX, we take 0.65 times our axial load capacity to find our phi PNX to be 280.4. We need to do the same thing in the y direction. So we're going to do the same thing for PNY with our EY of 4 inches. Plugging it into our equation, our moment is equal to our P times our eccentricity. We can find C. We can check all of our assumptions with this C and find that, again, all of our assumptions are okay. And then we can calculate our PNY with our given C. And we'll get a PNY here of 350.4 kips. Again, our bottom steel, our tension steel has not yielded, so we're still compression controlled. So our phi is 0.65, and 0.65 times 340 will give us our phi PN Y here. We need to then find our pure compression capacity. We'll use our minimum eccentricity limit. We found this before to be 420.3. And then we can solve for our phi PN using the Bresler Reciprocal Method, where we just have 1 divided by our phi PNX, 1 plus 1 divided by phi PNY, minus 1 divided by phi PN naught. So, and phi PN naught is our pure compression without any eccentricity on it, or yeah, our pure compression, assuming that the load's applied in the center of our column. And we can find our phi PN to be equal to 179.3 kips. So if we were designing the column, we would need to keep the applied axial load with this, or applied at these eccentricities under 179.3 kips to satisfy our design limit here. So that concludes our example problem.